Okay, this is the third video on solving Conics questions, and this one we're going to focus on solving the problems in the parametric form of the equations. We'll have the same problem as we've had before, a semicircular arch, and we want to know how high is it at 1.8 meters wide. This time we're going to solve using the parametric forms of the equation, which are for a circle, the radius cos theta for x, radius sine theta for y, plus their respective x and y shifts. Let's move it out of the way, give a bit of room, and let's go to it. So we need to attack this problem pretty much the same way as the other one, which is we're going to have to find the x value. So we take our 1.8 meter wide and we divide it into 2 of 0.9 from the center. 1.8 becomes 2 of 0.9, and since the center is 1.1 in, we have our x value that we're going to use at 2, and our y value is what we're going to try and find. X value of 2 to find the y value, and we can't use that for the meantime. We have to just use the x function and substitute in that x is equal to 2. Then we solve that by moving the 1.1 across, and then we calculate what theta is, and theta is 0.613. So when x is 2, theta is 0.613, and we can substitute that theta back into our y, and there we have it. 0.613 is going to yield our y of 4.33, and so that makes the arch 4.33 meters high at that point, which is fortunately the same as we got when we solved it the other way. And that's in general how you solve by parametric equations. You solve either for the x or the y depending on which one you're given, and then you put that back in and you get your answer. Now we could also have written our parametric equation in the simpler form, and then it's 1.1 cos theta, 1.1 sine theta with no shift. They are hidden, they're still there of course. So solving now becomes much easier because our problem is that we have 0.9 from the center is our x value, and we can find the theta, and note that the theta isn't necessarily the same theta as we found it in the other version, and we put that back into our y, and that yields us that our y value is 0.63. But of course our y value is not the height, it's this y value with the 3.7 y shift hidden. We put that back in and we get the correct answer, 4.33. Now I don't actually think that it saves any effort to do it this way. I think with parametric equations you're actually better to have the x shift and the y shift built in. That's one of the advantages of solving via parametric equations. They're simpler as long as you understand what's happening. You take an x value or a y value, you find the theta or t as it is sometimes, and then you put it into the other one to yield the answer. And because they are more straightforward without the squares and square roots of the standard form, they are usually the easier form to solve. There is a problem with this method though, and that is that when you solve a trig equation you only find the value nearest zero, which might not be the correct solution in context. And I'll give an example to show you how this can go wrong. We can take a ellipse, and it's 8 wide, 4 either side in this direction, 4 high, 2 either side in that direction, and its center is 5 across, 3 up. And we're asked to find the x value for when the y value is 2. So we are trying to find the x value for the appropriate y value, and we have the y value 2, we substitute it in and we solve that. Move the 3 across, minus 1. So theta is the inverse sine of the minus 1 divided by the 2, and that tells us that theta for this solution is minus 0.5236. We stick that into our x value rather, because we've defined the appropriate x value for that y value, and the answer is 8.46, which is clearly wrong. Except that it's not really wrong. What it is it's this solution, because there are two solutions for when y is 2, one on the near side, one on the far side, and our inverse sine calculation here, what that did was find the nearest one to 0, which is out this way, and so yields the answer 8.46. So what we've got to do is we've got to correct for that. So how do we do that? Well, what we do is we allow for the fact that the solution is symmetrical about the center point. The center point is 5, that's our 5 shift, we don't really need to calculate that, and that distance is the 4 cos, and we're going to flip it round. So instead of being positive, it's now negative, and that yields us our answer of 1.54, which is the correct answer. So when using the parametric equation, be very careful that when you solve for theta, that you are solving for the theta in the right quadrant. On your formula sheet, if you need it, you are provided with some formulas that help you find second solutions. Unfortunately, they are these, and they're very difficult to understand. So if sine theta is equal to sine alpha, then the relationship is that they are n pi apart plus this hideous thing here, slightly easier for the other two. In practice, you only want the one other solution within 2 pi radians, and that's this. For sine, it's pi minus the first solution. For cos, it's 2 pi minus the first solution, and for tan, it's pi plus. What you need to do to generate those is to stick n is equal to 1 in each of these equations, and you will get the correct answer. So you don't need to worry about multiple solutions, you just need the first solution, which is when n is equal to 1.